Okay, guys, so today we're going to talk about radians. Okay, so radians are essentially another way that we can measure angles. So most of the time we measure angle in degrees, especially in the real world, but it becomes advantageous in math to use a separate type of measurement, which is measured in radians. Okay, so first we'll talk about what radians are, and then I want to be able to convert from radians to degrees and degrees to radians. We'll talk about the length of a circular arc in radians. We'll talk about how to find the area of a slice of a circle, right? So like a pizza slice. And we'll talk about how to find the coordinates of an endpoint for a unit circle that correspond to a certain angle in radians. Okay. Now, the way that we're going to define radians is to be a unit of measurement for angles, and we're going to be given that 2 pi radians corresponds to a rotation through the entire circle. Okay, so if we have the unit circle here, then if I go all the way around one time, that is an angle of 2 pi radians. Okay, so from there, we're going to talk about sort of the relationship between radians and degrees. Okay, so we're going to convert each of these to degrees based on what we have so far. Okay, so if I draw a coordinate plane, try to make it nice and big, then our unit circle right on top of it, and we're going to say that if I have 2 pi radians, just like before, that's 1 full rotation. All right, so we know that this is 1 full rotation. But what do we know about a full rotation in degrees? We know that that's 360 degrees. So from this, we can say that 360 degrees and 2 pi radians must be equal, right? Because they each represent 1 full rotation. Okay, so that was part A. Part B wants us to do something similar, but for pi radians. Okay, well, if I went from 2 pi to pi, I would have to cut that in 1/2, right? So if I go a full rotation in 2 pi radians, I'm going 1/2 of a rotation. With pi radians, right? Now, of course, in degrees, what's 1/2 of a rotation? That's 180 degrees. All right, so pi radians would correspond to 180 degrees. So we could say that from here to here is pi radians. Okay, and then last but not least, we want to do pi over 2 radians. And of course, this would just be cutting in half again. So this would be 1/4 of a full rotation. Right, so this is 90 degrees. Right, because from here to here, you know that's 90 degrees, and it's also pi over 2 radians. Right, and it turns out that the most convenient relationship is this one right here, where we can say that pi radians is equal to 180 degrees. Okay, well, let's talk about this. So now, if we know that, well, let's put it this way. So 30 degrees, if I put that over 360, right, it just becomes a matter of reducing 30 over 360 to give me how much of a rotation this is. And this would, of course, be 3 over 36 it's equivalent to. So this is 1/12 of a rotation. Right? So 1/12 of a rotation in radians is 1/12 of 2 pi. So this is 2 pi over 12, or pi over 6 once we reduce it. And this, of course, corresponds to 30 degrees. This was part A. Now we can do a similar thing for 45 degrees. If I put 45 over 360 degrees, right? If you verify the math here, you can check that this is 1/8 of a rotation. Right? Now, if I take 1/8 and multiply that by 2 pi, I'm going to get that that is a pi over 2 pi over 8, which is pi over 4 radians. So that's 45 degrees. All right, and then last but not least, we could show something similar with 60 degrees. And of course, with 60 degrees over 360, that is 1/6 of a rotation. So I can take 1/6, multiply that by 2 pi, and that's a 2 pi over 6, which is of course pi over 3 radians. So that's 60 degrees. Okay, so those are some conversions from radians to degrees. And these are 3 popular angles that you should be fairly familiar with. Okay, so it would not hurt to become very familiar with these. Okay, so we sort of summarize our findings so far in this table. And again, like I said, usually the most convenient one to keep in mind is that 180 degrees is equal to pi radians, right? And that's present in these formulas here, which allow you to go back and forth from radians to degrees. And the idea here is that you can think of, if you have pi radians equal to 180 degrees, to go from radians to degrees, you would be given something in radians. And of course, you want degrees to come out. And I'm going to multiply by something that's equal to 1, right? I'm going to multiply by 180 degrees over pi radians. So if I do this, my radians cancel out, and I would get 180 over pi, right? So if you want to go from radians to degrees, you're just going to multiply by 180 over pi. So that way that your radians cancel out. And for the other case, if you want to go from degrees to radians, right, you're going to be given something in degrees this time, and you're going to multiply by something that's not going to change it. You're going to multiply by pi radians over 180 degrees. So that way your degrees cancel, and then you have pi radians over 180. Right? So that's sort of the idea of converting back and forth here. Okay, so now let's take one that's maybe not so obvious. We want to convert, let me write this a little bigger. We want to convert 7 pi over 90, and this is given in radians, and I want to convert this to degrees. All right, well, if I want to go from radians to degrees, I want to multiply by something that's going to cancel my radians, so I need my pi to be down here and my 180 to be up here. So now my radians cancel. One thing that's also nice is that my pi's cancel. And if I look at 90 and 180, these two terms here, I have a 180 up top and a 90 down below. So I can reduce that to a 2. And then I just have to worry about this 7 here. So it's 2 times 7. That would give me 14 degrees. All right, so the nice thing about converting from radians to degrees is that usually you can get those pi's to cancel most of the time. All right, now let's convert 11 degrees to radians. Well, to convert from degrees to radians, I need to take this, and I need my degrees to cancel, so I need 180 degrees down here and pi radians up here. All right. Now, when we multiply these, usually we leave the pi in there. Oops, my degrees cancel. And we can say this is 11 pi over 180 radians. And if you can reduce this fraction, so if it's possible to reduce 11 over 180, then we reduce it. But in this case, I don't think we can. Okay, so normally you can just leave it in this form. And of course, you would want to reduce the fraction if you can and leave the pi in there. Okay. Okay, so now we can relate a lot of the things that we talked about degrees, a lot of things that we talked about with degrees to how do they correspond to radians. Okay, so now if you have again, so positive radians would indicate that you're going a positive angle. So you're going counterclockwise. And if you have negative radians, that would indicate that you're going clockwise. All right. And again, we're still starting from the positive horizontal axis. Okay. So in this example, we want to look at the radius of the unit circle corresponding to negative pi over 4 radians, negative pi over 2, and negative pi radians. So the first one was negative pi over 4 rads, negative pi over 2 rads, and negative pi rads. So in general, the easiest way to do this is to convert it to degrees, since that's what we're more familiar with. And then we just plot the degree measurement, right? So if I wanted to do negative pi over 4 radians, if I put that into degrees, I would do negative pi over 4 times 180 degrees over pi radians. This is in radians. So my radians cancel, my pi's cancel, and I get negative 180 over 4. So that would, of course, be negative 45. Okay, so if I wanted to plot negative pi over 4 radians, that's the same as plotting negative 45 degrees. Right, so that's measured clockwise from the origin, so here. So this corresponds to negative 45 degrees, which is also negative pi over 4 radians. All right, similar idea for negative pi over 2 radians. I would want to convert this by multiplying by 180 over pi radians. So my radians cancel, and then I would have my pi's cancel as well. And then I'm going to get negative 180 over 2, which is negative 90 degrees. So if I come this way, again, since we're negative, I need to go clockwise. Then I get that negative 90 degrees is this radius, and this is negative pi over 2 radians. All right, last but not least, for negative pi radians, if I convert this is the easy one. My radians cancel, my pi's cancel, and I just get negative 180 degrees. So that's going to be, again, negative, so I want to go clockwise, and that will correspond to this radius here. Oh, sorry, this is just pi radians. All right, so those are a sketch of several angles for radians here. All right, now let's look at this in the positive direction. So now we have pi radians, we have 3 pi and 5 pi. Well, we know that pi radians from the conversion factor is equal to 180 degrees, all right? So we know that pi radians, and again, this is now positive, so we're going counterclockwise now. So this is my radius that corresponds to pi radians. All right, but what do you notice about part B, 3 pi radians? Well, this is pi radians plus 2 pi radians. But this is a full rotation. So for 3 pi, I'm going to go around once and then come back to pi radians past the starting point again. So this is also 3 pi radians. All right, and again, what do you notice about 5 pi? This is pi radians plus 2 times 2 pi radians. So this is 2 full rotations. All right, so this one is going to go around once, around again, and then come around here. So this same radius also corresponds to 5 pi radians. And that sort of brings us to the point that's related to our degrees. Oh, wait a minute. So this is sort of the same idea. So let's do it real quick before I explain the result here, just to drive it home. So again, we know that pi radians is out here. So this is pi radians. And if you look at negative pi radians, this is pi radians minus 2 pi radians. So this is go to where you were, but undo it by a full rotation. So what this really means is that we're going this way, negative pi radians, right? So this is also negative pi radians. And if I have negative 3 pi radians, that's the same idea. That is pi radians minus 2 pi radians. All right, so that's backwards, a full rotation, and then back to here. So this is also negative 3 pi radians. Okay, so now we get to the point, which is what I wanted to make a second ago, is that if you have an angle given in radians on the unit circle, then just like in the degree case when we could add any multiple of 360 degrees, we can add any multiple of 2 pi radians, right? So is also an angle. The same angle, I should say. Right? So adding any multiple of 2 pi to an angle in radians produces the same angle. All right, so that's sort of the point here. All right. And again, what's nice about radians is that in the degree case, the circular arc, right, so this is in degrees, we know that the circular arc was theta times pi times r over 180 degrees, right? Now, if you wanted to convert this to radians, we would take this theta times pi times r over 180, and then I would need to multiply by 180 over pi, right? Right, because I want to convert this to radians, right? So what would happen here is that the 180s would cancel out. I think I actually have this reversed, right? Yeah, I do have this reversed. Yeah, I need that this is theta times 180 times r over pi, right? Yeah, so then when we convert this to radians, okay, this makes more sense. I would need to take theta times 180 times r over pi, and then when I multiply by pi over 180, my degrees would cancel, my 180s would cancel, and my pi's would cancel, and I'm just left with theta times r. And if I'm on the unit circle, then this is just theta. All right. So the advantage of using radians on the unit circle is that the angle is also the length of the arc. And that's a powerful result to have, right? So if we're talking about an angle or we're talking about the arc, if you're using radians, then those two things are going to be the same. Okay. So we can look at an interesting example with a clock here. Okay. So we're going to just suppose that the distance from the center of this clock to the endpoint of the minute hand is 1 foot. So we have that this length is 1 foot. Okay. So we can essentially think of this as our radius being equal to 1. All right. Now we want to know what time is it when the endpoint of the minute hand has traveled pi over 2 feet since 10 a.m. So if it went pi over 2 feet, that's like it traveled pi over 2 radians, which is that it traveled 90 degrees. Right? So if we go from 10 a.m. and we advance it by 1/4 of a rotation, or 90 degrees, that's going to bring us to 1 p.m. Right? Oh, I'm sorry. This is the minute hand, right? So the minute hand has traveled this. No, I'm thinking the hour hand. Okay, let me erase this. Now, if the minute hand went 1/4 of a rotation, that means that we went 15 minutes. So, of course, that would correspond to a time of 10:15 a.m. All right. Now, in part B, we have that the minute hand has traveled 2 pi feet. But that's a full rotation. So if the minute hand went around 1 full rotation, that means that we went forward by an hour. So then we're now at 11 a.m. All right. Part C, if we went 3 pi feet, that's a full rotation and a half, or 1.5 rotations. So that means that an hour and a half has passed and we would be at 11:30. Now, finally, in part D, we're going from 10 a.m. to 12:15 p.m. So this means I had to go 2.25 rotations. Right? So the 2 full rotations are 4 pi, and the extra 1/4 of a rotation is a pi over 2. And of course, if I add these together, find a common denominator, I'm going to get a 9 pi over 2 feet. All right, so that's sort of an interesting problem relating to a clock that can allow us to use radians. Again, the idea that we can use radians stems from the fact that if you're using radians, then the distance you've traveled is the same as the angle. All right, so that's a nice sort of connection there. Okay, now we can talk about the area of a slice using radians. So if you want the area of a circular slice, that's equal to 1/2 times theta times r squared, as long as theta is in radians. All right, and that gets you the area of a circular slice. So as an example of that, we'll say that a 14-inch pizza is cut into 8 slices of equal size. So 8 slices of equal size. Okay. Now, if they say it's a 14-inch pizza, that's referring to the diameter. So then that means that we have a 7-inch radius. So r is equal to 7. So now if I want the area, the other thing that I need is the theta, right? Now, if I have 8 slices, that means that for one slice, theta is equal to 1/8 of a rotation, right? And in radians, that means that I need to do 1/8 times 2 pi. So that would, of course, reduce to a pi over 4. So now if I combine these two things into my formula, I'm going to get that the area is 1/2 theta, which is pi over 4, times my radius, 7 squared. And now it's just a matter of reducing this. So of course, if I square 7, that's 49. And I also have a pi up top. And then in the bottom, I have 2 times 4, so that's an 8. So this would be 49 pi over 8. And this was given in inches, so this is square inches. All right, so that would be the area of one slice of a pizza for a 14-inch pizza. And if you're curious, what's 49 pi over 8 look like? So 49, if I type this into a calculator, let's see, times pi, and I divide that by 8, you'll get that each slice is roughly 19.24 square inches. All right, so that's the idea. Okay. Now, of course, just like we can relate points on the outside of the unit circle to degrees, we can also do the same for radians, right? And these are just a couple examples of doing that. Okay, so let's do an example where you don't have a nice angle to work with, right? And this will be the last one of this video. So we want to find the coordinates that correspond to 14 pi over 3 radians. All right, now usually what I suggest is convert this to degrees, since that's what we're more familiar with, and then we can go from there, right? So first of all, let's convert 14 pi over 3 radians into degrees. So I would want to multiply by 180 degrees over pi radians. So my radians cancel, my pi's cancel, and if I take 3 and I divide it by 180, I'm going to get 60. So then I get 14 times 60, and if we multiply that, we get 840. All right, which is, of course, more than one full rotation. So if I subtract 360, that's going to give me 480. So still more than a full rotation. And if I subtract 360 again, that gets me 120 degrees. So that's not a full rotation. Where is 120? Okay, well, here's 90 degrees, and this is 180 degrees. Okay, so 120 degrees is going to be 30 degrees past 90. So this length here is 30 degrees. Now, when I drop my perpendicular down, okay, and I have my right triangle here, what's this angle in here? Well, that's a 60-degree angle, because this is 60 degrees, which makes this a 30-degree angle. And of course, this is my right triangle. Across from the 30, I have a 1/2. And across from the 60, I have a square root of 3 over 2. Now we have to be careful here, because we're interested in this coordinate. Now my y value is fine. My y value is square root of 3 over 2. But my x value isn't just 1/2. It's on the left side of the vertical axis. So this is a negative 1/2. All right, so the coordinate that corresponds to 120 degrees, or again, this was given to us originally as 14 pi over 3 radians, would be the point negative 1/2 comma square root of 3 over 2. All right, so that concludes this video on radians. I hope you enjoyed, and I will see you next time.